Good evening, everyone. My name is Nadita Joshi. I am a senior product security engineer at Zendesk. In my day job, I work on web applications and API security. And Of late, I've been thinking a lot more about AI security because it's everywhere. And that's really what leads me to present this talk to you today. My talk is titled Securing a Generative AI Implementation. So, yep, let's get started. On the agenda for today, um, I'm going to be starting off with talking about what we're working on. And the goal here really is to demystify Gen AI and, sort of enable all of you to be able to visualize what we're talking about when we talk about our LLMs and Gen AI implementations in your organizations. So we'll go over the building blocks with the demo application that I worked on uh, and talk about the architecture of your Gen AI implementations. Once we have that, I'll move on to talking to you about some of the Gen AI attack vectors. So this is really about discussing what can go wrong with this architecture that we're looking at. And with that information, I think we'd be in a good place to discuss some of the mitigations and security best practices. And finally, I'll close it off with some takeaways and discuss a little bit about what it means to approach Gen AI security holistically. So what are we working on? Um, when you talk about an LLM, let's think about what it means to build your LLM from scratch, right? Um, on a broad level, you can conceptualize this into three key phases. So you have your framework, you have your optimization, and then you have your agent. In your framework, what you're really talking about is your model architecture and your data preparation and the training environment, the basic infrastructure that you need to run all of this. So this establishes the base on which your model is going to learn and perform. When you talk about optimization, at this point you have a pre-trained foundation model, and what you're going to focus on in this space is improving your model's performance through fine-tuning and adjusting all of the different parameters that make your model useful. So at this point is where your model kind of learns and improves its ability to generate coherent and contextually relevant text. So this stage is pretty key to deploying your applications when you need them for very domain-specific use cases like healthcare or finance and things of that sort. And finally, you have your agent. So at the end of your optimization is where you have your agent that's kind of ready to be deployed, right? So then you have your agent, which is what's really going to be interacting with your web applications and your APIs and integrating with all of these different services to make your implementation available to end users on one end and enable all of its interactions on the back end with other services that it needs to interact with. Okay, so Um, two images over here. This is really just to talk about the pre-training phase of your Gen AI implementation. So what really are we talking about when we talk about pre-training? It's pretty key to understand what your LLM input data is. When we talk about pre-training, think of it as a text file that consists of, in my example, what I did was I took three open source stories, uh, no copyrights on the stories. You have to be aware of where you get your data sources from. So just three stories, a short text file. I trained my model on that, and that's what you're seeing here is the first stage of what happens when you're pre-training your data. And you don't really need to look at the code or any of the values or things on this screenshot. But I do want to talk about what's happening in your encoding and decoding phases with your pre-training. So your encoding, what it's really doing is it's taking all of this raw data from the text file that you have as your pre-training data set, and it's going to convert this into a numerical format that your model can make sense of. And then your model's going to work on this, and it's going to optimize it, and it's going to fine-tune its parameters. And um, your model pre-trains on this data set. It's going to learn the statistical properties of natural language. So that's things like grammar and understanding semantics and context and things of that sort. And finally, once you have your model that's pre-trained on this data set, it's going to do the opposite of your encoding, which is decoding. And then it's going to translate all of this numerical model outputs back to you into human readable text. When we talk about LLM architecture or we talk about a model, what we're really talking about is your transformer, and all of the different parameters that are optimized to make your model work. So what we're seeing here right now is it's a very basic GPT implementation. The model I used here is a GPT-2 small model, simply because I was running it on a local laptop and I needed something much lighter than your traditional GPT models. And this one implemented using PyTorch. And what really happens with your model when it's working with your data is it's taking your tokens that, the tokens that you had split through your encoding. It's taking those indices as inputs. It's going to embed them with some information that helps it. You can think of it as it's going through multiple iterations to make sense of the vocabulary that you provide to it, and it's building those relationships between all of the different words in the vocabulary. And then finally, you have your output logits, which would basically represent the likelihood of each token in your vocabulary. So before I move forward with this, a key point I wanted to highlight from this slide is because of all this probabilistic way that your models are building sense of data, what you really need to remember is that the output you're seeing from your LLMs, they're not thinking. All your LLMs are doing is that they're predicting the next word based on the probability that it's identified based on its input and all of its training parameters. Back to this LLM architecture slide. So we've talked about your model and we've talked about what its parameters could look like. Your architecture and weights of your trained body, these also can be considered intellectual property in some cases. OpenAI, for example, right? They have such powerful GPTs. Those are definitely IP. But that's not really the only case. So even if you're using your open sourced models, you may at that point think that, okay, this is not IP because this is open source data. But if your model's training on sensitive proprietary data sets, then at that point, again, your architecture and the model you're training on is going to be considered intellectual property. The third thing I want to talk about is your data accuracy. It directly impacts your model's performance. So we have 3 images on the slide here. And what I want to highlight is in each of these cases, what I did was I gave it a stark context of a simple sentence. The sentence is every effort moves you. And we really want to see how it's going to complete this sentence. So what's the text completion going to look like? So when you have an untrained GPT-2 small model, it's an untrained model, right? So if you see the output you see in image 1, it's really showing you just gibberish. It's just a collection of letters. It's not even words that make sense. When I pre-trained on my small data sets and generated the output using that model, you can see that it builds out an output that it kind of makes sense. At least these words exist in the English language, right? It's not really making sense in that context, though. But when you look at your GPT-2 small model and run this input on the same pre-trained base that the model came with, you see that the response you get is it's quite fantastic. It makes sense. And really, what I want to highlight with this is that the quality and breadth of your training data, it directly impacts how your model is going to perform, and it's going to also impact the coherence and reliability of your model. Continuing with talking about data integrity, this screenshot here, it's just a screenshot of what your fine-tuning data set may possibly look like if you're constructing a model that's sort of an instruction-based model. And this is really the next step of your LLM, right? So you pre-trained your model, you have it, you want to tune it into your very specific context that you want your model to work in. So at this point, your model is going to adapt for very specific tasks. And once your fine-tuning is complete is the point where your model is ready for deployment. So hopefully at this point, you have a sense of what we're talking about when we're talking about retraining data sets and fine-tuning data sets and models. So with that knowledge, what we're going to move on to now is what's new with threat modeling your Gen AI implementations. So the most important thing to remember is that our LLMs are probabilistic. And for any given input, your LLM is going to evaluate the likelihood of all the different outputs that are possible based on the patterns that it learned during its training. So because your model is predicting a distribution of possible next tokens, what's really happening here is that you're providing input in natural language. Your model is going to have an infinite number of inputs. And for your infinite inputs, you're going to have infinite outputs. And you're going to have an infinite number of edge cases that you're going to think about, which is, I think it's a little different from how you work with your traditional apps today. You also have new assets that you need to think about. You have your models and your data sets. In the context of Fed modeling your GenAI implementation, it's kind of essential to identify and protect all of these new assets that come into play. You want to protect you want to protect the asset itself, as well as secure how this asset is being used in the context of your GenAI application. So when we talk about our model, we're talking about things like your architecture, your weights and biases that are used, your optimization algorithms. And we're also talking about things like how your model processes its input and output, and whether it includes safeguards against malicious inputs and edge cases. When we talk about data sets, we're talking about all of our pre-training, fine-tuning data sets and embeddings. We're also talking about the integrity of this data. So where is this data coming from, and can it be tampered with? Interactions. There are new interactions with your LLM model. So if your LLM model is going to be interacting with plugins, and then those plugins are going to be interacting with other services or other plugins, all of these are new, I would say, attack vectors that you need to think about. And I think it's pretty common for LLMs today to be doing this, because your LLM in many cases is probably trained on a certain data set, and then you also want to be able to enhance its capabilities by pulling in information in real time. And the second thing with your new interactions is also your two-way trust boundary that you have with LLMs today. So it's not just that we cannot trust the client to LLM data flow, but also the LLM to client output that we see, because it's using natural language. And this is different from your traditional web apps, where you typically have your user controlled input, yes, but your outputs are likely to be derived from established business logic and data that's stored in databases and places where you have options to encode that data or sanitize that data before it's being stored. And it's a rapidly evolving landscape. You have new models, architectures, and training techniques. The field is evolving at a rapid pace, and the attack surface consequently is constantly evolving and expanding. And this just leads to an environment where you're going to have diverse threats that you need to think about, and there's always going to be need for continuous adaptation. At this point, I think we're in a good place to have understood what we're working on, and we'll move on to thinking of what can go wrong with this. So before we get started by what can go wrong, we need to think about the context in which we are considering our CLEP modeling. And for that, we need to understand your shared responsibility model with your AIs. So what we're seeing up here is, what we're seeing here really is you have your IaaS, PaaS, and SaaS. So IaaS is infrastructure as a service, PaaS is platform as a service, and SaaS is software as a service. And these are really the different kinds of service models that you would have when you're working with your LLMs. So take for example OpenAI and its ChatGPT. If you're using the WebUI version of it, you're working with a SaaS implementation. In very specific niche industry cases like finance or healthcare, where you may have you want to rapidly develop your AI models, but you also want to have the capacity to scale on demand as it's required, you're more likely to be using something like a PaaS or a platform as a service infrastructure, where what you really have is your AI compute infrastructure is definitely managed by a third party, and then you have a lot more control over the model training data and the training, the data sets that go into it, and how that LLM is implemented and used by your end users. So with these baseline assumptions in mind, what your Gen AI application can really look like is something like this. So what we have in the center, the LLM agent, the model, the training data, we've kind of talked about that while talking about building an LLM from scratch. And then on the left-hand side, what we see are all of the different application services. So this is really all of the different services that your LLM agent is going to interact with, where your application then is going to deal with all of its customer data and manage all of its other user interactions, things like a web UI or a chatbot that interacts with end users. And on the right side, what we have are your downstream services that your LLM agent is likely to interact with. So these are all of your different plugins and extensions. Okay, so now we're going into identifying what can go wrong. And what I'm doing here today is we're going to take an asset-based approach, and then we're going to look into the data flow and think about your input output, and then talk about all of your other interactions. So starting with the model, there are two ways that you need to think about what can go wrong with your model. The first is theft of your model or replication of your model, and the second here that I'm going to point out is the thinking about the context in which your model is being loaded and used and how that can go wrong. So model theft is nothing but the unauthorized access and exfiltration of your LLM models. Standard OWASP top 10 LLM um, vulnerability. And what this can really look like is, think of your models as something that you've stored in your software version control systems. So take GitHub, for example, and then if you have a misconfiguration in your network access and an attacker has access to this model file, that's really what we're talking about when we talk about model theft. When we talk about model inversion, it's a little different. You're kind of stealing the model, but you're not really stealing it's the file directly, right? What one way that you can do it is you're querying your LLM with a large number of um, prompts, and then you take the responses from those prompts, and then what you do with that is you use that as synthetic data for your own model and continue training that model up until the point where you think you have um, it's mimicking kind of the model that you wanted to mimic. And at that point, you've created a shadow model, which is it's a near replica. It's a theoretical approach, I would say, at this point, but it's likely to be a replica of your proprietary model at that point. And um, yeah, so that's another way to steal your model. And finally, malicious code execution. Here, so like in the example that I spoke about in the first two slides, that we were talking about like, what your model looks like, right? Uh, I loaded the models with transformers using, I loaded my transformers using PyTorch. And PyTorch, the way it loads is when it's loading your models, it's really just using your serialization functions underneath it. And if you have unsafe serialization functions, for example, like an unsafe method such as the reviews method in your pickle module, then that's another attack vector where you could be opening up your entire environment to attacks such as remote code execution simply because of the way your model objects are being loaded and unloaded in your environment. Next, after models, I want to touch a bit upon the data. And with data, again, we're dividing it into two different categories. So you have your data poisoning, which is basically altering or tampering with your data itself to create a malicious data set. And what this can really do is it can introduce vulnerabilities, backdoors, and biases in the output that comes from your LLM. And then the second thing we want to think about with data is sensitive information disclosure. And this could be unintentional as well as intentional. So that's really what we're going to look into. With data poisoning, one example of it is the bot that was designed to learn about language um, over time from its environment, that Tay the Twitter bot. I don't know if everyone's kind of familiar with that, or you might have heard about it at some point. Yeah. Okay. So this was like way back in 2016, right? When Microsoft decided to release Tay the Twitter bot. And Tay was just supposed to be 19, it was really supposed to mimic a 19-year-old American girl, and all the bot was supposed to do was learn from the users that it interacts with on Twitter. And it sounds really nice and sweet, but obviously it's like in retrospect you want to think about it and you're like, of course it's the internet and you can't have good things. So if really just went from being your friendly fun bot to a VR nightmare in less than 24 hours, because at the end of all of those interactions it had learned on all of this data that it was getting from the internet, and it had started generating pretty harmful content that Microsoft definitely didn't want their bot to be producing. So yeah, so that's an example of data poisoning. Moving on to sensitive information disclosure. Black box risk in models that touch proprietary data. What really does that mean, right? So in your SaaS environment, you could be using models that you don't have any control over what training data, what data sets your model is training on. So that's the black box aspect of it. So take, for example, you have an OpenAI implementation in your organization. So you're all using ChatGPT, it's all good. You have HR and legal and sales, and everyone's using all of these things. But what if what if your third party model is training on all of this data? Then what that means is that as your model is training on this data, all of this organization specific information is going to be added into your model's memory. And then this is one way of having your sensitive information disclosed to other users of that model outside of your organization as well. When we talk about the second category with sensitive information disclosure is unintended data loss. But we're going to look into two ways that this can happen. So one is your misconfigured tenant architecture. In this case, again, think of it as you have a SaaS model, you're making queries, you have a subscription to your SaaS model, and you're one tenant. There are multiple other organizations that are also tenants that are using the SaaS model. So let's say that I, as an attacker from inside my organization, I query this model and I'm making requests to it. It's working as it should, but say it has a tenant ID in its request that I can modify, and then that gives me access to a different tenant's data as a result of misconfiguration on the side of your SaaS provider. So that's one risk we need to think about. And then the other one is overscope privileges, and this you can really think about it more from an internal implementation in your organization point of view. So think of it as say you have a custom GPT GenAI implementation, and what it's really doing is you want it to read data from a very specific Slack channel, for instance, and work out of the data that it gets from that. But as a result of overscope privileges, what you could end up doing is that your chat GenAI implementation may have access to all the different channels across your Slack instance, including private channels that it shouldn't be accessing. And that's another case of unintended data loss that occurs as a result of overscope privileges in how your implementation is configured. The third, so now we've talked about our ASICs. We're moving on to the very nature of your LLM models and how it deals with your input and output. And the first set we're going to talk about is prompt injection. So, quick show of hands, how many of you have heard of prompt injection already? Everyone, right? Almost. It's like the star of your LLM attacks. But yeah, so your LLMs can be coerced into performing unintended actions. And it sounds really cool, and it can be pretty dangerous. So there are two ways that you could go about doing this. You can have direct prompt injections and indirect prompt injections. So direct prompt injections can be something as simple as me supplying inputs through my prompts and overriding system prompts that my GenAI implementation is supposed to be working on. And indirect prompt injection, you really have to think about you're really trying to target vulnerabilities in the way your LLM itself integrates or communicates with other backend services, and think of how you can manipulate that. So, for example, maybe your LLM integrates with a database on the backend that you don't otherwise have access to, but then you use prompt injection to kind of get your LLM to access this database and input information into it or modify information in it. The next threat that you think about when you think about input output is over reliance. And over reliance is really because humans have a tendency to overestimate and over trust the LLM's capabilities. It is just what it is. I don't know, but yeah, I think people tend to trust LLMs a lot more than what they really are capable of. And this means that LLMs, which hallucinate due to their very nature, is something that humans can inherently trust, because LLMs have a tendency to sometimes supply inaccurate information with extremely high confidence. And humans are going to trust this and go with the data that they receive. An example of this would be LLM generated source code. So if you're generating source code, I have tried doing this with LLMs previously, and yes, sometimes they do generate good code, and in some cases, I've seen them completely break the application that I'm trying to build. And yeah, they do also introduce security vulnerabilities in some cases. So this is stuff you don't want to be relying on an LLM for. The third is denial of service. And denial of service, you can think of it as overwhelming your processing capabilities of your LLM via resource consuming queries. And what's really happening when you do this is that you could end up impacting your output. You could end up having a high cost of usage of your LLM and overwhelm the organization itself. And you could also end up impacting the availability of your LLM model for all of the other users in your organization. One way of doing this is repeatedly sending long inputs to the LLM, which exceed its context window. So what really does that mean, right? So what really is your context window? So your context window is it represents the length of all of the text your model can manage and work in the context of. This includes your input as well as output. And the size of the context window really influences how well your LLM is capable of managing complex, lengthy, and nuanced conversations and tasks. So the larger your context window, the better your LLM is going to work, right? But what happens if you max out this context window? As your context window fills up, it needs to start prioritizing what parts of the context, what parts of the information it has, it needs to maintain, and what parts it needs to drop out. And in the process of making this decision, it might end up dropping out pretty critical and information such as the original prompts and guardrails that you provided as system inputs to your model. In this case, you're really it's a right attack vector for getting your model to generate unexpected and exploitable outputs. Finally, we have all of our other interactions and what are the things that can go wrong with these. So you have your plugins, and this is where you have your OWASP top 10 LLM, OWASP top 10 for LLMs threat of excessive agency, right? Excessive agency is you're giving all of these plugins. These plugins may have broader privileges and broader access than you might think they have. Overprivileged plugins, take an example of you as a user, you're using an LLM and your LLM is speaking to something like you're using Drive to manage your documents. Maybe you just wanted to read your documents. You're using a plugin through an LLM, you're using your plugin through your LLM, you want to read documents from your Google Drive. But your plugin has access to perform actions beyond reading stuff from your drive, and it can also read and modify documents. So in this case, you have an overprivileged plugin. You're using it for the purpose you want to use it for, but it is also something that an attacker could misuse and perform unintended actions. Another case of excessive agency is when your plugins can approve high impact actions without verification. And what this means is that let's take the example of cloud environments. Say you have an AWS environment, you're uploading all of your login data. It's a simple task. You want your plugin to upload all of your login data into your environment, and that's really all you wanted to do. But for in this instance, it could be likely that your plugins had access to perform a lot more actions, such as interacting with compute resources or interacting with your S3 files, interacting with other resources where you might typically require multi-factor authentication if you were making changes there as a user. But your plugin may actually bypass this step and perform all of these actions. So this is another case of excessive agency where you can misuse this to perform actions that you would otherwise not have the privileges to perform. Vulnerable supply chain. So this is really just about everything that comes as part of implementing your LLM and your GenAI implementation. So simply getting your LLM set up has so many dependencies. You have your deep learning frameworks, you have your NLP libraries, and you have your data processing libraries. In addition to that, you have all of your typical traditional third-party package vulnerabilities, and then you have your malicious plugins to think of, and any vulnerable or deprecated models and poison data sets. So there's a whole lot of different um, attack vectors that can act as, that are just like posing as some threats to your LLM implementations. So we've talked about what can go wrong. Next is, what are we going to do about it? Here we're going to continue looking at these emerging threats from your Gen AI context, and then I'll move on to some of your more AppSec specific mitigations. So taking all of the examples that we've already looked at from your previous slides, take the example of your LLM model theft. And a quick note about the mitigations here. It's kind of mapped 1:1, but obviously one mitigation is not going to fully mitigate that threat in its entirety. So what you really need to think about is, uh, think of it as a defense in depth approach where you want to be implementing all of this to ensure that your threats are kind of mitigated successfully. So in the case of an LLM model theft, what you really want to think about is ensuring the right access controls to limit your access to the LLM model repositories and all of your training data sets. Um, in the case of your shadow models where you had your LLMs being replicated, uh, one thing that you can think of is API rate limiting and using per user quota management. So this is not going to prevent an attacker from generating a shadow model, right? But it's going to deter them. It's going to slow them down enough to the point where it may not be worth the effort. Another mitigation that's being discussed in this respect is model watermarking, and watermarking is it's a technique to watermark your model. So enabling this would basically enable you to trace unauthorized copies and usage of your models. This is very similar. So think of it as it's very similar to what you would do with your identifying copyrighted images by embedding pixels in them. So something very similar to that. Um, another thing that could help with your models and ensuring that you don't have all of these different queries successfully being made to replicate your proprietary model is something called robustness testing. And robustness testing, really what it does is it's going to test your model's effectiveness to detect extraction queries. Um, it's not on here, but it's going to come at a later stage as well. It's just one of those mitigations that help with many different threats. Uh, in the case of your model objects being serialized using unsafe methods, of course, you want to rely on your traditional secure coding best practices. You want to check inputs before unpickling. If possible, you definitely want to maintain a whitelist of all of the different methods that you can serialize and unserialize, and you want to use safe libraries. And another thing that really helps in this case is sandboxing. So that would really reduce the blast radius in the event of your model being able to uh, model environment being able to perform code execution. All right, we talked about models. Now we're going on to data. So take the Twitter bot. Okay, that's just a bad idea in general. Don't use crowdsourced data for training your models. But then what should you do? Use trusted vetted data sources, and each should be carefully selected to ensure that your initial training is helping you establish a foundation of acceptable language use. And you also want to ensure you have content moderation. So what this really means is that you use NLP techniques to detect and block offensive content. Another mitigation here is adversarial robustness techniques, such as federated learning. And what this really means is, instead of training your model on, so you want to continue training your model on user supplied data, but you want to be able to vet that data before your model trains on it. At the same time, you want to give your users the capability to continue working with models that are trained on their information. So here you use decentralized training sets that are local to your users' devices, such as your smartphones and your IoT devices. And what you can do here is your user can continue using their training data set that's if your user can continue using your training data set that's kind of trained on your local data, but you have the option to upload it on a central repository. The central repository has the option to vet this data and reject it if it's required. So this kind of reduces your chances of poisoning your data. You also have data anonymization techniques that you can use to ensure that you're filtering out any PII. And then tenant isolation and access control measures. These are your typical AppSec mitigations. Moving on to other interactions, you want to ensure that the plugins that you use implement effective access control again. For any sensitive actions that are being performed by your plugins, you want a human in the loop to approve these actions. And for your supply chain, you have all of your typical best practices around vetting your plugins, using model and code signing, and all of your software composition analysis for your traditional open source components and dependencies. So up until now, we kind of talked about all these emerging threats and mitigating them. But this screenshot here is really an example of your LLM model, not a failure in your LLM model, but using your LLM model to attack an organization only because of your traditional AppSec best practices failing. So what we're seeing here is a Sysdig threat research team's observations about an attack that they investigated. And this attack, it's now known as LLM jacking. And what really happened here was there was a vulnerability in your open source PHP framework. This allowed arbitrary code execution. And then this gave attackers access to cloud credentials. They used these cloud credentials to enumerate all of the different LLM models present on that cloud service provider. And at that point, they were the attack was identified and it was stopped. But really, what your attackers could have continued doing was actually using all of those LLM models. And in this case, considering that they were targeting Anthropic's cloud model, it would have cost the victim company about $46,000 of LLM computation costs per day. And that's huge. And this is all not happening. So there's no novel attack here. This is simply your regular AppSec best practices failing. And this is where you need to think of all of your traditional AppSec best practices, and they still continue to apply even more so within the context of your GenAI implementations. And here what I have is a checklist of all of your different AppSec best practices, but how they relate to your LLM models. So when you're talking about encrypting sensitive data, you also need to think about your LLM models and data sets. When you talk about secrets management, you want to also store your LLM API keys in secure storage. Access control and network segmentation are pretty critical to ensuring secure use of your LLM implementations. And that's where you have things like least privilege and role-based access controls and things on your network controls, network segmentation and controls such as isolating your LLMs from public networks, preventing data scraping by restricting your network access, and sandboxing your environment that's running your LLM models into hardened containers and VMs. Along with that, you have your typical source code management best practices, which ensures that you have version control system on all of these different assets that you're storing, and you have accurate access controls to ensure that you're using only validated code, and any changes to this are tracked. You also have your standard input and output validation best practices, so things that you want to do to prevent common attack vulnerabilities like SSRF, for example. If you have an LLM that's going to take user supplied URLs and then query that to predict and give you like the most updated weather information, then you want to make sure that you're sanitizing all of these URLs that you get and not have it give it the capability to also query IP addresses in your local network. And you also want to, of course, add in contextual output encoding wherever your data is being presented to an end user. This is your standard XSS vulnerability mitigation. Using secure third-party libraries and frameworks, this is again crucial because, as we saw earlier, there's a whole bunch of different supply chain risks that come in your GenAI implementations. And then you also want to consider adversarial testing and monitoring over time. So all of these attack vectors from your AppSec point of view, and you obviously also have to talk about your AI systems management. your AI lifecycle management, your plugin lifecycle management, and an AI BOM or an AI bill of materials. So AI lifecycle management, because this is a probabilistic system that's constantly evolving, you're going to always have drift in your model's performance as well as your training data sets. So you need to continuously adapt to this through continuous updates. And because of the fast pace at which everything's evolving here, you're most likely to end up with models and data sets that are in need of deprecation at some point, and you need to ensure that you do the security. With your plugins, you need to think of your plugins lifecycle management. So you have your inventory management. You want to understand all of the different plugins that your LLMs are interacting with, and you also want to have a sense of all your zombie plugins. So if you think of plugins, they're very similar. They really, at the end of it all, they're just API calls that are being made from one system to another. So it's all of your API security best practices that are going to apply here. So similar to how you have zombie APIs and shadow APIs, you're going to have zombie plugins, and you're going to think about identifying and managing these. So they'll be good. So yeah, we've talked about what we worked on for today, what can go wrong with it. We talked about some ways of securing this. Did we do a good job? You tell me. I think this is a starting point. It's not comprehensive, but this is a place to get started. We do need to talk a lot more about AI, LLM security. And really in your threat modeling 4-step approach, the final step, of course, which we're not going to be talking about here, is going and doing the actual work of talking about all of these threats and mitigations with your teams, and then verifying these mitigations and ensuring they are working as expected. And this is really a continuous cycle that you want to have on an ongoing basis. Before closing out for today, we've talked all this time about AI from a product security and application security point of view, but obviously with AI, you're not just talking about secure use of your data, you're also talking about acceptable, unbiased, and use of AI in a manner that's safe for the people that are consuming this information. And what all of this really means is that you want to be in compliance with all of your regulations. You want to ensure adherence to industry regulations to maintain compliance throughout your AI lifecycle around things like data privacy protection. You want to prioritize user data privacy. You want to ensure there's ethical and legal oversight on all of these AI implementations that you have. And in the cases where you're using your third-party vendors, you want to constantly be vetting all of these vendors and ensuring that they are also following your security best practices, and they're also following the same standards that you're holding your organization to. And at the end of it all, you also want transparency and accountability around the use and deployment of your AI systems. And what all of this means is you can't function alone to secure your AI systems. You really need to work together with all of your different teams around that work with things like compliance and legal and governance and vendor security. So at this point, we're at the end of the presentation. We're almost there. Just a few key takeaways from today's talk. AI has the potential, and it really is kind of fundamentally changing how we interact with the world around us today. I'm sure everyone's using AI in some form or the other as, just a buddy to brainstorm with, or at work to develop code, or, everyone's doing it. So you really want to, when we think about implementing these AI systems, you want to start secure early, because there are very heavy costs involved. There's a lot of compute resources and time and money that goes into training and building these models. So you want to start with secure data sources, and you want to ensure that you're starting with secure models so that you don't have to deal with re-implementing these at a heavy cost at a later stage. And you want to perform context-aware risk prioritization. We talked about a lot of different risks, and not all of them are equally applicable in every implementation, right? You need to think about your shared responsibility model. You need to think about what are the different interactions that your AI LLM implementation has in the context of your environment, and then perform your risk prioritization accordingly. Your application security best practices, they still continue to apply, and even more so with your introduction of AI. And last but not the least, your fair and secure use of AI really requires a comprehensive cross-functional approach to AI deployments. It takes a village to build your AI implementations, and it takes a village to secure them as well. These are some of the references that I used for preparing for this talk today, and I really found all of these incredibly useful. So if you're interested in learning more about AI, LLM security, and sort of going down that rabbit hole, I think these resources are a good place to start. All right. Yeah, that's really all I have for you today. Thank you.